My name is Shimazu of the University of FUJI, Japan, and my talk today is here it is written the design study of a passive residual heat removal system for molten salt system FUJI. FUJI is, I will explain in later a little bit in detail. And this study was or has been done by one of my master students, Takahiro Ishiguro, co-author of this presentation. I will briefly explain the evaluation code, evaluation of the cooling system, and the specification of the design. That means what our objective for the design. And I will explain some example of parameter survey, and finally I explain one of the design example. And finally, I'll explain the concern of subcriticality in the drain tank, because we are going to use coolant, water coolant. So water coolant is a good modulator for the nuclear reactor system. So we have to check the subcriticality. And finally, conclusion. First of all, environmental and natural resources. The environmental problem is global warming. We have to keep global temperature as a favorite temperature zone, and uranium supply is not enough, expected by breeding, and as a result, the thorium utilization is now attracting focus, as discussed in this conference. Thus, we are focusing on thorium-based molten salt reactors. And the other one is the safety. I think you all know that Fukushima Daiichi accident was a very disastrous accident. And it tells us that the importance of cooling and confinement of fission products under the station blackout. And the most important thing is the residual heat removal for a long period. If Fukushima succeeds this residual heat removal, then that kind of disastrous nuclear accident can be avoided. That means we acknowledge that importance of passive safety features. That means with station blackout. With station blackout, we cannot expect any electricity power or other force of cooling the decay heat. So our objective of this design study is to evaluate residual heat removal system by a passive cooling system under the station blackout without any help of another power source. And this is, as I explained, that one of the lessons learned from the Fukushima accident. And in our MSR, discharging fuel salt to drain tank can empty the fissile materials and the fission product from the primary system. Then, if we can keep or maintain the integrity of this drain tank, that means if we could succeed the residual heat removal, then the whole plant can be maintained safely. This is our objective of the design study. What kind of specification or limitation we have to establish or set up for the design study is we establish two objectives or specifications. One is the maximum coolant temperature must be less than boiling temperature. And the next one is the maximum fuel temperature. I mean, the fuel temperature in the drain tank is not greater or higher than the 750 degrees Celsius. At the molten salt breeder reactor, the exit temperature, exit fuel temperature is about 700 degrees Celsius. So we set a little bit higher maximum temperature as 750 degrees Celsius. And this is the configuration of target system FUJI. Here, I think you may be familiar with this figure, but here, this is the drain tank and freeze valve. And if some accident or abnormal operation occurs and the fuel temperature is going up, then the freeze valve is melted and all the fuel salt can be drained into the drain tank. The primary or main design parameters of FUJI 2 is shown on this table. The thermal capacity or thermal output is 450 megawatt, and the electric output is 200 megawatt. And say the type of fuel is like that, same as that molten salt breeder reactor developed by ORNL, and the composition is also the same, almost same. And this FUJI is a thermal reactor, so we use graphite moderator. And the other parameters, I think you may well aware. And power density is of FUJI 2 is lower, 7.3 kilowatt per liter. And reactor vessel is a little bit larger in considering this power output, thermal output. Okay. And evaluation code to calculate the cooling system or RHR system performance. We use thermal hydraulic code NetFlow++. This is developed in a university by Professor Mochizuki. The development of plant dynamics analysis code NetFlow++. And this is one-dimensional thermal hydraulics analysis code. And this code has been verified through analysis of Monju, the Japanese prototype fast breeder reactors, and its residual heat removal system. They analyze performance and compared with the measured temperature transient. And this is another bird view figure of the FUJI 2. Like this is a drain tank. And our evaluation model is this time is very simple. The reactor has clamps, and station blackout occurred, and freeze valve opens, and fuel drained to drain tank. Then we start calculation. But in actual plant, it may take we have to analyze the transient, how long that would the fuel salt take to be completely drained into drain tank, and during that period, maybe coolant temperature or fuel temperature or cooling tube temperature may change. But this time, as the first step of evaluation, we just simply assume that the calculation can be started after the fuel has been completely drained. The modeling of the RHR system is very simple. This is drain tank, whole drain tank, and we use coolant tube. We set coolant tube in the fuel tank, and the coolant is gathered to pipe and go to the air cooler and go back to the tank, drain tank. This is coolant is circulated by natural convection, so we have no pump or motors. And like this, fuel outside and in the fuel coolant tube are going through. And heat source in the fuel. This is very clear that the decay heat, we can take into account not only decay heat. The decay heat is, we assume that infinite irradiation time and decay heat from actinide, and also we have taken into account the correction factor for the neutron absorption of fission products. And this data are recommended as decay heat and recommendations. This is Atomic Energy Society of Japan, a little bit older, but yeah, a little bit older. And we use decay heat of uranium-233. And the total decay heat looks like this. This 1 second after the shutdown, and go down to less than 1% after 1 million seconds. Now, next, I'm going to explain the candidate of coolant. The same analysis or evaluation has been done by ORNL. And they also try various kind of coolant. Here, the water and steam, and their evaluation is water and steam excellent as coolant, and ease of circulating, required volume excellent and good. But when it's boiling, the pressure may go high, and conclusions suitable for cooling possibly best. But actually, they don't adopt water. They adopt NaC or sodium, but in order to get that conclusion, they tried various few salt, fluoride, carbonate, or nitrate, and some various salts, and the performance looks like almost good, excellent, good, some condition. This must be filled with nitrogen atmosphere and something like this. And I show you, I quote the conclusion of ORNL. It says, although water appears to be a fairly attractive coolant, provided a double barrier is used in the drain tank cooling tubes to avoid thermal shock following a salt drain, and to give better assurance that water could not reach the fuel source. Calculations showed that it would be difficult to fit the required number of tubes into the drain tank head. I will show you later some drawing. A compromise was therefore reached, which employs the natural circulation of FUJI salt mixture through the drain tank tubes, and then cooling of the salt by radiative heat transfer to boiling water. This is the conclusions of ORNL at the time. This is the top view of the drain tank, and you see this small diameter looks like the line, but these are all coolant tube, and the diameter of the tube is about 0.5 to 0.75 inches. That means about around 1 centimeter to 1.5 centimeters or 2 centimeters diameter, and I think you can understand the expression. And this small coolant tube go into the tank, and this is the only this showing only four tubes. This is U tube, and it looks like they distribute the U tube under this a little bit larger tube or pipe. So that it would be difficult to fit the required number of tubes into the drain tank head. That is the reason why they did not use water as coolant. But in our case, it is different from the molten salt breeder reactor. One difference is total decay heat, and the second one is the total volume of pure salt. So we re-evaluate water coolant. Water is, as you know, they don't freeze if it is the temperature does not go below 0, and it's not so expensive and very easy to handle. So we re-evaluate the possibility of water coolant. And as we select the water, that we set the limitation of water coolant, and we set the limitation that the temperature should not go boiling point. That means 100 degrees Celsius. And the initial temperature of the coolant is, we assume 40 degrees Celsius. We assume that the higher temperature because the water may reach boiling point when the initial temperature is higher. So we take into account the hottest coolant temperature. That means in the summer, during summer, maybe 40 degrees Celsius can be expected. So we set the conditions like this, and we, before I go into the design study, we try to reduce thermal shock. And temperature difference stress is a function of K. K is the ratio of radius of this is diameter, or inner diameter or inner radius versus outer diameter. And when this value approaches 1.0, then the thermal shock can be reduced a little bit, maybe 20%. So in our case, our K value is around 1. And thermal shock, evaluation of thermal shock, we use standard formula. You can find some textbook of heat transfer or mechanical dynamics, and this is coolant outer tube outer surface, and this according to this formula, the temperature at the initial point is 634 degrees. This is average fuel temperature of normal operation, and the water temperature is 40 degrees Celsius. So, and the surface temperature is evaluated to be around 200. And for the tubing inner radius of 30 centimeter and the thickness 1 centimeter, we can calculate the stress, the radial thickness, and actual stress about 82.4 megapascal. And we calculate total stress. It's 82.4, and permissible stress of tank material of Hassel N, or that means we interpolate at this temperature. The permissible design stress is 133 megapascal. So this is the permissible stress is larger than the evaluated stress. This, of course, this doesn't include any uncertainty or factor, but less than the allowable stress. So now we said the thermal shock can be tolerated, and other stress due to fuel salt weight or some other can be negligible, small in comparison with these values. And in our design study, there are a lot of parameters for the cooling system, like drain tank system, the unit fuel volume surrounding unit cooling tube, and geometry of the tank, and the volume of coolant, number of air cooling tubes, and fin of the tube coolant, the air cooler fin, and the outer diameter of the fin, or thickness of the fin, and the number of fin per unit length, and height of air duct, and the representative length of air duct. We combine these parameters by kind of trial and error calculation procedure. One of the example of our parameter survey is this is shown for the fin diameter and the effective length of some 3.5 meter case and 4 meter case, and diameter of fin, and you can see the temperature, water temperature can saturate around the fin length of about larger than 14 centimeters. So like this kind of parameter survey we did, and finally we designed, we found out reasonable combination of parameters. This is design of FUJI, and coolant volume, length of pipe, diameter of pipe, that means fuel diameter, and diameter in tubes, and thickness of tubes, and tank height, and air cooler, number of tubes, 1040, and tube length, and so on. And here is transient of coolant temperature. First of all, the temperature go up higher, up to say 90 degrees Celsius, and then the coolant, the natural circulation begins, and the temperature go down, and go down, only going down. So the maximum temperature does not reach 100 degrees Celsius. And the fuel temperature looks like this, and it begins at 643 degrees Celsius and go up to 700, maybe 30, 40 degrees, and go down, only go down. And this red line shows the fuel salt the melting point. So if the temperature of fuel salt go down below this temperature, the fuel salt may fuel salt solidifies. So at this moment, we did not take into account the solidification, or the fuel salt becomes solid. We did not take into action or any countermeasure, but this time from the beginning of the station blockout to the melting point is about 2 days. So it may be said that, oh, it can be enough time, but when we consider Fukushima case, it is not so long. So if we have to keep the fuel salt temperature higher than the melting point for example, for more than 10 days, then we could close the air cooler duct, depending on the fuel temperature and on the time after the shutdown. So the transient is very small, and so that I believe that this temperature can be kept around or above the melting point for certain days. The final problem to be discussed is the subcriticality. As I explained at the beginning of my presentation, that there's fuel salt and coolant, diameter 30 centimeter. So if the original ORL design, they use coolant as a FUJI, then I think the modulation of FUJI is not so good as graphite or water. So when you drain all the fuel salt in the drain tank with FUJI salt in a coolant tube, I think it is the criticality will not be expected. But in our case, we use water as coolant, so it may become critical. So we calculated a nuclear design code, extreme PM, and the condition is height is infinite height, and the horizontal boundary condition is reflective. So the result is K infinitive. That means infinitive multiplication factor. And we take out what this one cell and calculate. And K infinity at the temperature 20 degrees Celsius is 0.37. So we don't have to take care or worry about the criticality. Okay. Now this is a conclusion that passive removal heat, diffuser heat removal system based on water coolant can be designed. And one small item, the aeration may be required for the coolant water because it reaches to boiling point temperature. It may reach. Thank you very much for your kind attention.
Hello, Martin van Staden from Steenkampskraal Thorium in South Africa. I have actually a number of questions. First of all, this coolant tank, it's an active safety system, is that correct? So it's got pumps that are cooling providing the coolant flow?
It's caused by natural convection.
Only natural convection. Okay. And then the second question is, what is the temperature of the cooling vessels of the outside of the cooling tank?
Outside? Yeah.
Of the tank. If the fuel is peaks at 700, what is the vessel temperature?
Outside temperature we do not take into account this time.
Now of the vessel, the steel vessel.
Only the fuel salt temperature is cooled down by the natural circulation water.
Okay, but what I'm saying is if the vessel temperature, if the fuel temperature is at 700, the vessel will be at about 500-600. So, yeah. Is that correct?
No. The outer temperature is 700. Inner temperature is 500. The average temperature is 640.
Hi, I'm Mark Halper. I'm a freelance journalist. I'm here blogging for the Weinberg Foundation. There was some talk yesterday about the freeze plug, the plug that melts when things get really hot. And there was some talk from some other presenters that they weren't sure yet that freeze plug will do what it's expected to do, that is melt and prevent a meltdown. And it's a very simple system, and simplicity can be wonderful in an age of complexity. So how confident are you in the freeze plug?
I think it's out of our ability. I think as the ordinary concept design they also say, or the Dr. Yoshioka also discussed the freeze valve reliance and the time to drain the fuel salt into the drain tank. It depends on the freeze valve. So we have to take into account to improve that the fuel salt can go down drain tank as soon as possible. It may be our problem to solve.